Okay, let's take a look at section 1.6. So we're going to talk about n-dimensional geometry. So we're familiar with R2 and R3, but we're going to talk about Rn. So a vector in Rn, it's just an ordered n-tuple of real numbers. So instead of just A1, A2, A3, we have A1 through An. So that's what we mean by a vector in Rn. So here's a vector in R5, and here's a vector, the n plus 1 tuple. So we have 2n, 2n minus 2, 2n minus 4. Anyway, this is in Rn plus 1, I guess, depending on n. Okay, now we talk about what we mean by two vectors are equal, even in Rn. It's the same idea as for R2 and R3, if they have the same components in the same order. It says if AI equals BI for all the I. We can also talk about addition and scalar multiplication. So if we take A plus B, we, just as before, we add them component by component. We do scalar multiplication, we do it this way. That is, multiply each component by k. We can also do the dot product in Rn, like this. So they say we can't make a picture in more than 3 dimensions, but nonetheless, we can use analogies to define the length of a vector in Rn. So just like before, when A was in R2 or R3, we said the length of the norm was this. We can continue with that because we do have A dot A even in Rn. So we can do this. And then we can also do distance between two vectors, which before we said between A and B was the difference between them and then the norm. So we can still do that same thing because the norm is defined in Rn like this. And we can define the angle between two vectors because this was the formula for the angle between two vectors in R2 or R3. So these operations are still defined for Rn. So we can still do this in Rn. So we're just going to say that if we have two vectors A and B in Rn, we can do this. We can take the inverse cosine of that. So we're going to call that the angle between these two vectors. Now, it's not quite the same thing as the three-dimensional, of course, but we can still use this formula to have an angle. And just a note that there are many possible thetas. For example, if this was equal to 1, then basically we're saying the cosine of theta equals 1. That would be true for what? Cosine of theta. In other words, if this worked out to 1, then this statement is the same as this statement, and the cosine of theta equals 1. There are many thetas that will give you that. For example, theta equals 0 will do it, but theta equals 2 pi will do it, and 4 pi, and so on. So there are many thetas. So we're just going to, they say here, we're going to take theta between 0 and pi. So we're not going to, so in that way, otherwise this would not be a function, right? Because you'd have the cosine of 1 could be many different things, or I'm sorry, the inverse cosine of 1 could be many different things. That's not a function. So we want this to be a function, so we'll just limit the thetas, and then it is a function. But they say that this may not necessarily be between 1 and negative 1, but in order to take the inverse cosine, it has to be between, this has to be true, otherwise we have a problem. So, because remember that the cosine function is always going to be between 1 and negative 1. So that means this needs to be 1 and negative 1. It says, fortunately, something we're going to prove in a minute, takes care of this issue. So now that we have the concept of the angle between two vectors, even in Rn, then even though we can't draw pictures of these vectors, we can still say that two vectors are perpendicular or parallel, because we can talk about the angle between them. Or we can also talk about how far apart two vectors may be, because we have a notion of distance. Now, she does mention that this theorem from before, this was in section 1.3, says that A dot B equals this, but this is kind of circular now because we don't have an independent meaning of theta. It's defined in terms of A dot B, so this is a little bit circular. Then she says that here. Okay, there's no simple generalization of the cross product. We can create a standard basis of vectors in Rn. So remember we had I, j, and k in R3. So this is the analogy in Rn. So remember that I in R3 was 1, 0, 0. So in Rn we have 1, 0, 0, 0, and so on. And E2, or what we called J before, was 0, 1 like this. And we keep going till En. These are called the standard basis vectors for Rn. They're analogous to Ik and j in R3. And just like before, we could write an arbitrary vector A, which might look like this in terms of I, j, and k. Now we can do an arbitrary vector A in Rn like this in terms of these. So it's easy to see that if you take A1 times E1, what do you get? You just get A1 here and zeros there. If you take A2, E2, you get 0, A2, and zeros. So you get A1 here, A2 here, AN here. And when you add all these up, you get this. Okay, let's go on. So here are two famous and often handy inequalities. So this one is called Cauchy-Schwarz inequality. So it's talking about A dot B and the absolute value of that. Remember, A dot B is a number, so the absolute value of a number is less than or equal to the norm of A dot the norm of B. So it's putting some kind of bounds or boundaries on the dot product, the magnitude of a dot product. The magnitude of the dot product is never going to be bigger than this times this. It could be smaller, never going to be bigger. So she says if we're just talking about R2 or R3, this is virtually immediate because of the theorem, this theorem here. So A dot B, if we take the norm of that, we have this theorem. If we take the norm of this, it equals the norm of this. And then we just want to say that this has to be less than or equal to just the norm of A times the norm of B. So that's obvious because this is at most 1, so it could be less than 1. So we get this result. So however, in dimensions larger than 3, we have to do it differently. So they first say if A or B is 0, then this is true because they're equal. So this is never bigger than that, this one. So we're going to assume that A and B are neither A or B is 0. So then we can talk about the projection of A onto B. And recall the definition, maybe you remember. a dot b over a dot a. So again, this is not 0, so this is okay, this part. And so we have this, and then we can say that that this is a scalar. So this is some number times a, so it equals ka. Here, k is this here. So let c equal b minus ka. Okay, so we're going to define c, some c, equal to b minus ka. So ka is this projection, and b is this b. Okay, this is kind of an arbitrary or kind of abstract. We don't know why they're doing this, is what I mean. But anyway, so b equals ka plus c. Then we have a dot c equals 0. So why is that? So a dot c equals a dot b minus ka. That's what c was. That's a dot b minus k dot a, ka dot a. That's a dot b, and we're replacing k by this. We have that, and that works out to this, I guess. Is that true? I guess, yeah, these are all numbers, so we can cancel, and then we get 0. So a dot c equals 0, okay. We leave it to you to check that the Pythagorean theorem holds, namely the following equation is true. Okay, so remember, this is the projection of b onto a, and we defined c to be b minus ka. So looking at this picture, we have b and ka, and then c goes between b and ka. That's the way we define c. So here's c. So we can, by the Pythagorean theorem, we can say, no, sorry, we can't say that. We have to check that this is true. I mean, it looks like it's true if we draw it like this, but we're talking about vectors in Rn, so we don't know anything about this. This picture doesn't exist in Rn. It looks right from everything, but it's just it's not Rn. So we don't know that this is true, but they say we can check that it's true. So I guess we have to look at the definition of C, which is b minus ka. So we have to put that in here, and hopefully this works out. So you can check that. Multiply this equation by this, which is this. So now we get a squared, norm of a squared, the square of the norm of a, and then the square of the norm of b, and we're multiplying this side, and by the same thing, each term. But then we have this, and this, and this. We have that, and then somewhere they're going to change this to this. And then we can cancel this with one of these, and I guess we end up with this and that. So then they point out that this quantity is non-negative. And so, what was this? This was this times this, the norm squared equals this and that. So the norm squared is, so this is non-negative. So that means that the left-hand side is bigger than just this piece, because we're dropping this piece, which is non-negative, so we can write greater than or equal to here. Now taking the square root of both sides here gives us the thing we were trying to prove, which was that this is less than that. So let's see that. I guess this is less than that, yeah. Okay, so that is, I didn't prove this, but I think that if we put b minus ka in here, we can show that this is true. Okay, so that's called the Cauchy-Schwarz inequality, and that's used to prove the triangle inequality, which is the next theorem, which says this. Now, if a and b are vectors in R2, then this says that if we have a triangle like this, here's A and here's B, then A plus B is here. It's the sum of these two. And so if this is just a triangle, of course we can say that the length of this is never going to be bigger than the length of these, than the sum of these two lengths. So the length of this means, that's how we write it, like this. And the length of this plus the length of this is this side. So this is never going to be bigger than the sum of those. So in R2, this would be, we can visualize it as a triangle, and that's why it's called the triangle inequality. And but we need to prove it in Rn. So strategic use of the Cauchy-Schwarz inequality. Again, what is that? It's that if we get rid of the squares here, it's that this is never bigger than or is less than or equal to this. The dot product of A and B is less than the norm and the norm. So let's remember that. And then look at here. So A plus B norm squared is the, remember the norm of A plus B is A plus B dot A plus B square root, but if we square it, we get this. And then this we can do some, we prove some properties about dot product somewhere back in section 1.2. So we can do this. This is legal for dot product. Then if we take the norm of A and B, this is the Cauchy-Schwarz inequality. So instead of A dot B, we're replacing by this, so we can write less than or equal to. But this is equal to, this is the norm squared, so we can write the norm squared here. And this is the norm squared, so we can write the norm squared here. And then all of these are numbers, so we can rewrite this like this just because of, we recognize this from regular algebra. So we have finally that this is less than or equal to this, or sorry, we have to take square roots. So this is less than or equal to this without the square roots. And they say we can take the square root because both sides are non-negative. Okay, so now we've proved the triangle inequality for Rn. So these two things turn out to be useful for various other proofs and explorations of Rn. Okay, let's talk about matrices again and see how we're going to denote them in this text. So a matrix is defined as a rectangular array of numbers. So we need a good notation for matrices and their individual entries. So we're going to use uppercase Latin alphabet to denote the entire matrix. So like this, A, and we will continue to do so. We shall also adopt the standard convention and use lowercase Latin alphabet and two sets of indices, one set for rows and the other for columns, to identify the entries. So here we have two sets of indices, like here M and N. The first index is for the row number. So this is in row M, and the second index is for the column number. This is in column N. And the shorthand for this, or for A, is, in this text, they're using brackets, and AIJ stands for this whole thing. Okay, so we're going to use this to stand for this, and also, of course, to stand for this. So then we also say that vectors in Rn can be thought of as matrices. And sometimes, they say we'll have occasion to write the vector A as either a row vector, meaning a 1 by n matrix, like this, or more typically as a column vector, like this, which is an n by 1 matrix. And we didn't use double indices here since there's only a single row, but we could use double indices here. But it would look a little strange, so this would be 1, 1, 1, 2, and 1, n, and so on. So we can say that a vector, we can view it as a matrix. And we can also take an m by n matrix and we can think of it as a vector of vectors. So what that means is here's the m by n matrix, but we're viewing it as a column vector of row vectors. So we have a row vector and another row vector and another row vector, another row vector, and then this is just a column of those vectors. So that's a little bit awkward, but so anyway, an m by n matrix, so this would have m rows, but only one column, but each column would be a row vector. Kind of strange to say this all, okay? Or we can do it just the opposite. We can say that it's a row vector of column vectors. And now we're going to talk about matrix operations. So addition and scalar multiplication are the basic ones, or the simple ones. So a plus b, if a and b are the same size, they're both m by n matrices, then we can add them, and we just add them element by element. We've seen this before. So here's a and b, a plus b, you take 1 plus 7, you get 8. You take 2 plus 0, you get 2, and so on. But if they're not the same size, if this is b, we don't add such things. And a plus b is equal to b plus a, and this is also true associativity. And the zero matrix with all zeros, is the identity matrix, we call it, for addition of matrices, because a plus 0 gives you the identical thing back again, gives you a back again. And then we have scalar multiplication, which means multiplying a matrix by a scalar, and that just means, like, if we multiply this matrix by 3, just means multiply each entry by 3. And then we have some properties for scalar multiplication. For example, if you take k plus l times a, you can do it this way. So it's a kind of distributivity. You take k times a plus b, you can do this. That's another distributivity. And this is associativity, kind of. So we can prove these things. Okay, now we get to the complicated one, which we've done before, but just let's see how they write it in this book. So this is matrix multiplication. So in that case, we put only certain kinds of matrices can be multiplied together. So if A is an m by n, then if we want to multiply another matrix B has to be an n by something. So M and P don't have any restrictions on them, but the first matrix, the n here, the number of columns has to match the number of rows in B. So otherwise we don't do this. So matrix product AB, then the size of the product, though, comes from the M and the P. So the AB will be M by P, and we've done this, but to multiply this matrix times this matrix, for example, one of the we'll take row by a column, and we do the dot product of this row times this column to get the different items in the resulting matrix. So, and this is the calculations, and I think we did this. So, for example, this one, so this one is a 2 by 3 and a 3 by 2, so the result is going to be 2 by 2. So if you want to know the entry that in the 2, 1 position, so you have to take this times this, and we mean the dot product of this row times this column. These both have the same number of elements, so we can do the dot product. And we do the dot product like this, and we get this, we get 47. So this element is 47, and we can do the rest of them as well. Now if we look at the reverse, that is B times A, then the result is not a 2 by 2, but a 3 by 3. And we get a different, we get completely different entries here. Now here, to calculate each entry, we had to do three terms. But when we do this one, we're only going to have to do 2 terms for each of these entries. So there's a certain kind of balance there. So even though this has more, this matrix is bigger, each of the calculations for this, and so on is less. So anyway, here we got this size, here we got this size, so clearly AB is not the same as BA. So it's not commutative. So here. Okay. Then we need some properties for matrix multiplication. So we don't have AB equals BA. We do have some other properties like A, B, C. You can do A, B, and then C. K, you can move the K around freely. There's this kind of distributivity with addition, like this, and also this kind of distributivity. So these can be useful, and we need to prove these. And then there's another operation besides multiplication, addition, scalar multiplication. There's something called the transpose of a matrix. So here's an example. Here's A. It has 2 rows and 3 columns. And the transpose, you just sort of flip it over. And so the first row becomes, in the transpose, becomes the first column. So here we have 1, 2, 3. Here we have 1, 2, 3. Second row becomes the second column. So that's called the transpose. This is called the transpose of this. So, or we can say that the Aij entry here becomes the Aij becomes the Aji entry here. So that's what they say here. Or they actually say just the opposite, but it's the same thing. And then, of course, if we flip it and then flip it again, then we just end up with what we started with. So that says that the transpose of the transpose is just A. Now here's another property that is not quite as obvious as the first one, as this property, and that is that the transpose of AB is equal to B transpose A transpose. Remember, we can't necessarily switch the order here, so otherwise it would look really simple. It's not quite as simple as that. Okay, so to show that this is true, what you need to do is consider the product of AB. Look at a general element in the product AB. So you just want to talk about, so you want to talk about AB equals some matrix C. C has a bunch of elements in it. Consider some arbitrary element Cij and write what it equals in terms of A and B elements. So you're going to have it's equal to some sigma of something. Then note that the transpose of AB, or the transpose of C, the Cij element, the transpose of that will be the Cji element. So you want to show that that is equal to the Cij element that you would get here. Okay, so she says that for this course, the transpose is mostly just a notational convenience for us. So, in other words, if you have the dot product of A and B, you can write, of course, we write it like this, which is like this. But we could then write it like this and this. So what does that mean? So here, this is just the dot product, but here we're talking about doing matrix multiplication. But this is matrix multiplication of a 1 by n and an n by 1. So that's going to result in a 1 by 1. And basically it's going to give you the same result as this, except it's going to be equal to a matrix. But we're going to kind of ignore the fact that it's a matrix. It's a 1 by 1 matrix. That's basically just a scalar, or we can think of it that way. So in that sense, the dot product can also be written as matrix multiplication of a matrix A, which it seems like it's not so important to distinguish between a matrix A and a vector A, but technically they're different. So this is a matrix A and a matrix B. But I think in this book, I'm not sure that we said it, but I think in this book, we're going to talk, when we talk about a matrix A, it's a vertical matrix. So I think that's the convention in this book, that a matrix A is a vertical matrix. So in order to get it like this, we have to do the transpose of it. That's why they're writing the transpose of A here, and then the matrix B. So it's a little bit confusing, but basically we just want, we're just saying that the dot product, which is between vectors, is basically the same thing as a matrix A transpose times another matrix B. And I think the reason why we have we need the transpose here is because if we just wrote A in this book, the assumption is that it's going to be a vertical matrix. So we don't want a vertical matrix. If it was a vertical matrix, then we'd have an n by 1, and that wouldn't work. N by 1 times n by 1 doesn't work. But 1 by n, n by 1 works. So that we have to use the transpose. Okay, in this example, they say consider something like this. So here's a matrix. It's an m by n, we can see here, because that's the, and here is another matrix, which is a vector, well, it's a n by 1. So we can multiply these two together, and we're going to get an m by 1. And we can represent this like this. So we have A times X. A is the matrix, and X is this. I guess we could think of X as a vector or as a column matrix. And now we can think of this as as a variable. So, and we can think of A as constants. So A is basically has constants, and X is like X contains several different variables. So really we can say that X is in Rn, right? It has n elements. So it's a vector in Rn. Now when we multiply A, this m by n matrix A, times this X, we just said we're going to get, somewhere we said, that we're going to get an m by 1 matrix. But remember, m by 1 matrix is the same thing as a vector in Rm, right? So we're going to get something in Rm. So we start with something in Rn, start with X in Rm. We multiply it by this big matrix here, and we get out something in Rm. So we can think of doing this as starting with something in Rn and transforming it into something in Rm. So this is like a function with this many inputs, n inputs, and what comes out is something in Rm, so with m outputs. So we can say this is a function from Rn to Rm, because we take things in Rn and we get out things in Rm. So that's what they say. They say this is a function from Rn to Rm. So that's what we call it a mapping. A mapping is another word for a function. Now, it's called a linear function because it's kind of similar to what we think of normally as a linear function. So this is a linear function when we just have a function from R to R, right? We just have when we take just a number here, and we get out a number here. But this is linear, right? We call this linear. Actually, sometimes we'll call, of course, ax plus b linear, but we're not using the word linear in that way. So it's a little bit different. So anyway, but this is also linear in the same sense that this is linear, but this is a little bit, well, anyway. So what we really mean by linear is that it has this property. That's what we mean by linear. That's what's meant by linear now. So, well, you have to check, is that true? So if you took this vector x and you had another vector y of the same, also an n by 1, and you add them and then apply f to it, in other words, then multiply it by this matrix, is that the same thing as taking this x, multiplying it by this a? That's what this would do. And then taking the y and multiplying by a, because that's what this would do, and then adding them. So is it the same to do it this way as that way? In other words, if you add the x and y first and then multiply by a, is that the same thing as multiplying a times x and then a times y and then adding the results? If it's true, we call such a function linear. So this is our function. This is our function. So is it true for our function? So it's not, f doesn't have to be multiplying a matrix times x, but in our case, that's what f is. But the question is it linear? So does it have this property? And there's one other property of a linear function, and that is this true? So if you take k times x and then and then put it into F, which means then multiply it by A, is that the same thing as um, putting X into F, which means multiplying X by A, and then multiplying by K? So this has to be both of these properties. If they're both true, then we call such a function linear. And this does have that property. So I'm not sure if we show that here. No, she doesn't show that here, but you could show it, and that would mean that it's linear. Now, there's one other kind of interesting. So she's trying to explain here why we define matrix multiplication the way that we do. And she says that basically it's because when you do this, you can write expressions that involve matrices and vectors that look like kind of normal algebra. Like this is normal algebra that kind of looks the same. And just like we have what we call function composition for single variable functions, we also have function composition for these kinds of vector valued functions. These are called vector valued functions, or sorry, F is called a vector valued function, basically because the output is a vector. We said the output is in Rm, so the output is a vector. By the way, we also call F a multivariate function, and that term is used when the input is a vector. So in this case, the input is a vector and the output is a vector. So because the input is a vector, we'd call it multivariate, and because the output is a vector, we'd call it vector valued. So that's a little bit confusing, but that's just the language that's used. So F is both multivariate and vector valued because the input is a vector in Rn and the output is a vector in Rm. But now they say, suppose we have F is as just defined, and G is another apparently multivariate vector valued function because it goes from Rm to Rp. So the input is a vector and the output is a vector. It's another, and suppose that G is another linear mapping. Now, linear mapping doesn't mean that it's a matrix multiplication, but it turns out that actually you can prove that any linear mapping is a matrix multiplication, but we'll ignore that now. Just saying it's a linear mapping means that it does this. So G also has this property, and G also has this property. So G is another, but she says here, it is a linear map of matrix multiplication. Okay. Anyway, suppose it also, so it also has these two properties. Then if there's a composite function, G circle F, which goes, remember now, F goes from where to where? F goes from Rn to Rm, but then G goes from Rm to Rp, so that works, right? You put in X into F and you get something in Rm, but G takes Rm objects, so that's okay, and outputs an Rp object, so that all works. So then, so that's a composite function. Suppose we have a composite function that does that. So this is what we mean by composite function. It turns out that it's going to be, the composition is going to just be, remember, G is defined by B with B, and F is defined with A, and this composition is just going to be the matrix multiplication of B times A. Okay, so that's a very nice property, that it turns out that if you have a G is Bx and F is Ax, then their composition is just going to be Bax. So that is a nice property. We have to show that all of this is true, but that is a nice property, although you may not recognize it as such right now. The other thing is that G circle F, if both of them are linear, and that means basically that both of them are consist of matrix multiplication, then their composition, as we just said, is BAX, and that is, but BA is a matrix, so this is also, so the composition is also going to be linear. Okay, now before we saw the equation of a plane, and it looked something like this, but this is what we call a hyperplane, the equation of a hyperplane, because it's in n dimensions. So remember that this was, remember when we just had A1, A2, and A3, then this was the equation of a plane. Now we can write this like this if we define a vector A equal to this and a vector B equal to this, then A dot x minus B, I'm sorry, and x is this, then A dot x minus B is exactly this up here. So equals 0 is x equals 0. Now recall that we can, this is a vector, but we can treat it as a matrix. And then if we take its transpose, we can rewrite this as this equation here, where x is also x and b are also matrices instead of vectors. So we can call this the equation for a hyperplane in Rn through the point B, where B is this so-called point with normal vector A. So this would be the n, or rather this would be the n dot that we saw before. Now we have A, which has n elements in it. Different n, by the way. Now here's an interesting statement. The points x that satisfy this equation fill out an n-1 dimensional subset of Rn. So that's kind of the idea that this is a plane. So going back to R3, then we said if we have R3, then this equation will be a plane. Well, how many dimensions would we say a plane is? We typically say a plane is two-dimensional. So it's a subset of 3 dimensions. So it's if in 3 dimensions, then the plane is two-dimensional. So we would expect that in Rn, the plane will be n-1 dimensional. Okay, next they show an example from economics, just to emphasize that this is, although this is quite abstract, there are lots of applications of this. So even though, we're talking about hyperplanes and Rn, but there are many cases where we might want to use this, and one example is in economics. So they say, suppose you have n commodities, n different commodities. So you might have gold and silver and diamonds and coffee and so on, n different commodities. And if we denote the price of the ith commodity as p sub I, then the cost of purchasing x units of that commodity is pi x sub I, right? Because let's say coffee costs $100 per something, and then you want to buy 10 of that something. Let's say it's coffee costs $10, and you want to buy 5 pounds of it, and it's $10 per pound. Then the cost is 50, 5 times 10. So we can define the commodity bundle price, I guess, or cost is p dot x, because it's this plus this plus this. It's the cost of buying all of those, which I guess is called the commodity bundle. Now suppose you have an exchange economy, so we may want to buy and sell items. So they call something an endowment vector. So this is somehow the amount of the ith commodity that you can sell. So this is the amount that you can sell of the first commodity and so on. Then I guess buy or sell maybe. So how much can you afford? So this is the most you can, I guess, buy. And so this is the most that you can afford. So you can afford any commodity bundle like this as long as it's less than or equal to that. But then we can rewrite this, just bring this to the other side. We can rewrite this like that, factoring out the P. In other words, you can afford any commodity bundle X in the budget set, where the set of all X, such that it satisfies this equation. But this is a vector equation, so that's something new, and that's nice. So the equation this defines a budget hyperplane passing through W with normal vector P. Okay, so that's just an example. Okay, the next topic is determinants, and we've talked about 2 by 2 and 3 by 3. Now we want to graduate to n by n matrices. So let this be an n by n matrix. Remember, we sometimes will use this notation. It just means the matrix. The determinant of this matrix is given by, of course, a real number, because the determinant should give us a real number. So we'll denote it by this, like that, as usual. And then we have to go through a lot of trouble here. But the idea is the same as before. Let's look at an example. It's easier to see it than getting caught up in all these subscripts. So, for example, if we have this matrix, so this is a 4 by 4. So what do? We take A11. So what happened to A11, by the way? Okay, they're skipping to A12 here, but here's A11. So this first part, you have this, and you have that. So we have this -1. We have 1, which I guess is A1, this element here. And then when we cross out this and we cross out this, so we're left with 1, 0, 5, this. So there's this one here. So that's the first one. Then they're showing us how to do the second one. So you start here at 2, you cross out this and this, so you're left with this, which is here, and you fill in, so it's this one here, you fill in all this stuff, so A12 is here, so you put it 2 there, and then you do the next one, you go down and over, so so anyway, they write it out. And then you see, though, that unfortunately, we have to figure out the determinant of this and this and this and this. So we have to do with this one, because it does say determinant of this. So we have to go cross out that, and we'll figure out the determinant of that, then cross out this, and figure out that determinant. So we have a lot of work to do. But if you keep doing it, you'll get down to a number, which we said it should be is a real number given by this. So that's what we mean. This is definition. So that's what we mean by the determinant for an n by n matrix. So some terminology here. The determinant of the submatrix Aij is called the ijth minor of A. So, okay, maybe we have to learn that language. So I guess this is called the ijth, which I would be, I guess, 1, 2. So the 1, 2 minor of A. And the quantity, and this stuff here is called the ijth cofactor. So this stuff here is called cofactor, and so on. So some language there we have to get used to. And this definition that we just looked at, this thing here, is called the cofactor expansion of the determinant along the first row. Right? We did expand it along the first row. So we did this one, we crossed out this and this. And we did this one, we crossed out this and this. So we're expanding it across the first row, they say. Then she says it's natural to ask if one can compute determinants by cofactor expansion along other rows or even other columns. And the answer is yes, although they don't prove it. So in other words, you could, so if instead of starting here, so cross out that and that, you could start here, cross out this and this, so you'd have this and this and this and this, and okay, so you could do that. So you can read through this to see an example of that. So then she says that, so here I guess there were some zeros, and so it's going to make the calculations very easy, but there aren't always such zeros, of course, in a matrix. And then she says, one does not compute determinants of large matrices by means of cofactor expansion. Instead, there are certain properties of determinants that are used to make hand computations feasible. And apparently they will be covered in the exercises. So here's a fairly obvious example. So it says, prove that a matrix that has a row or a column consisting entirely of zeros has a determinant equal to 0. Well, suppose this entire column was 0, then we're going to take 0 times the determinant of this matrix, and then 0 times the determinant of the other matrix. It's all going to be 0. But we also said that you don't have to just work with the top row for the cofactor expansion. You could use any row or any column. So the same can be said if you have zeros in any row or any column. Okay, so we also talk about certain kinds of matrices are called upper triangular. So you can see why this might be called upper triangular, because this part over here is all zeros. And then we can also talk about the main diagonal of a matrix, which just means here. Okay, so we're talking about square matrices, so n by n matrices. So the main diagonal is here. We can also talk about lower triangular, which just means all the top stuff would be 0. So then they say, here's an interesting result. If we have an upper or lower triangular matrix, what's the determinant going to be? It's going to turn out to be the determinant of the matrix is just going to be the product of the main diagonal. By the way, why is this the main diagonal? Because this is A11, whereas A22, it's here, whereas A33, it's here. So this is the main diagonal, the product of the main diagonal elements. And it turns out that if it's lower or upper triangular, that the determinant of the entire matrix will just be the product of these things here. So they ask us to prove that. Okay, so let's look at numbers 26 here, some properties of determinant. So these previous two exercises show that it's not difficult to compute determinants of even large matrices, provided that the matrices have nice form. So if they're triangular, you just have to do this, and if they have 0 row or 0 column, then it's just 0. So the following operations, called elementary row operations, can be used to transform an n by n matrix into one in upper triangular form. So these are going to be, we're going to be able to take any matrix, most matrices, and transform them into upper triangular. If we can do that, then determining the matrix of the result, the upper triangular one, is easy. So what are these operations? They're called elementary row operations. So you can take a matrix and you can exchange two rows. So for example, here we have this matrix, and what do they do here? They put this row on top and this row second. So they switch these two. Okay, so that's one of the so-called elementary row operations. Next one is multiply a row by a non-zero scalar. So we can take, let's see, what do they do next? So they're going to add, well, so we could just multiply this row by 3. So we get 3, 21, and negative 6. So that's also called an elementary row operation. Another so-called elementary row operation is to add a multiple. Oh, it has, by the way, when you multiply a row, it should be non-zero number that you're multiplying by. But add a multiple of row I to row j. So that's what they did here. So they said add negative 1 times row 1 to row 3. So we have this row, we're going to multiply it by negative 1. So this becomes negative 1, this becomes negative 7, this becomes plus 2. We're going to take that and add it to here. So I guess what happens, so this doesn't change, you're just going to multiply this and add it to here. So this doesn't really change. This doesn't change, 2 is not changed. But what happens, we take negative, we add negative 1 to 1, we get 0. We add negative 7 to 5, we get negative 2. And we add 2 to 9, we get 11. So that's an example. That's another example of an elementary row operation. Okay, so there's 3 elementary row operations that they're talking about. And they say that you can use these to put something that originally was not in upper triangular form like this one into upper triangular form like this one. It doesn't always work, but you can try. But they say the question is, how do these operations affect the determinant? So do these operations change the determinant? So maybe if they didn't change the determinant, then I could take this, transform it to this one, and then I could say, oh, the determinant is just 1 times 2 times 14. And if it didn't change from the original, then I could say the determinant of this was 1 times 2 times 14. The question is that true that it doesn't change the determinant? So they ask us to guess, make a conjecture as to the effect of each row operation. You don't need to prove your results are correct. Then repeat part A in the case of a row operation of type 3. Sorry, this means if we try type 1, that is this one, exchange the rows I and j, make a guess what happens, what the result is. Then what happens if you make a change of type 3? Prove that if B results from A by multiplying the entries in the ith row by a scalar, that was type 2, then the determinant of B is equal to C times the determinant of A. So they want us to prove that. So I just looked up elementary row operations and determinant, and I'm sure there are many discussions of this, but here, type of elementary row operation, ERO, elementary row operation. So multiply a row by a constant C. So what happens is the determinant is multiplied by C. Add a multiple of one row to another row. Doesn't change the determinant. Interchange two rows, the determinant changes sign. So you can go through the proofs of these 3, but we'll just take it as fact that the determinant is multiplied by C when you multiply a row by a constant C. If you just add a multiple of one row to another row, nothing happens to the determinant. And if you interchange two rows, the determinant changes sign. So with that information, we could try to take this, what is this, a 5 by 5 matrix, and make it upper triangular, and just record what we had to do, each of those elementary row operations, how many we had to do and what they were, and then we could figure out the determinant of the new upper triangular, hopefully, as the product of the diagonal, elements, and then recording we're remembering what we had to do to get the upper triangular or lower triangular matrix. We could then figure out, sort of work backwards, and then figure out what the determinant of A is. So they say by using row operations to transform A into a matrix in upper triangular form, and by using the results of exercise 26 to keep track of how the determinant of A and the determinant of your final matrix are related. Okay, you can check this out. See if the determinant of this is the sum, the determinant of the sum of these two is equal to the determinant of the first one plus the determinant of the second one. On the other hand, they say that if A and B are any n by n matrices, if they're both n by n, then the determinant of their product is the product of the determinants. So they say use this fact to show that the determinant of AB is equal to the determinant of BA. So that's fairly easy because the determinant of AB is equal to this. Determinant of BA is equal to this in reverse order, but of course, whether you switch the order of this or not doesn't make any difference in terms of what it's equal to. Okay, here's the definition of a matrix having what we call an inverse. So a matrix, an n by n matrix, a square matrix, this is only true, again, for square matrices, is invertible or non-singular. It's also called non-singular. If there is another n by n matrix B, so that when you multiply A times B or B times A, both ways, you get the so-called identity matrix. So an example of the identity matrix is, well, it's a matrix that has ones down the diagonal and zeros everywhere else. Let's see if we have a definition. So here's an identity matrix for 2 by 2. For 3 by 3, it looks like this. For n, it looks like ones down the diagonal and 0 everywhere else. So, of course, the identity matrix, by the way, is upper triangular. So if you want to know what the determinant of the identity matrix is, since it's already upper triangular or lower triangular, we can just take the product of the diagonal, but that's just going to be 1. So we already know that the determinant of the identity matrix is 1. So going back to this concept of invertible, we say that a matrix A is invertible if there is another matrix B such that when you take the product of A and B, either way, either A, B, or BA, both have to give you the identity matrix. If that's true, then we say that A is invertible. If there is no B, we call B the inverse. If there is no inverse of A, then we say that A is not invertible, or it's not non-singular. I guess we'd call it singular. So, for example, they say verify that this is the inverse of this. So you just have to multiply the two of them together and check to see if you get the identity, the 2 by 2 identity. Here, they say verify that these two are inverses. That means you have to multiply them together and see if you get the 3 by 3 identity element. Now, this one is a bit more trouble. We have to find the inverse of this. Find the inverse of this. And here they say, try to find the inverse, and then they say what happens. So apparently it's not going to work. So this may not be invertible. And we can sort of see that from one of the facts that we just proved a little while ago. And that is, we just said that if you have a column or a row, which is 0, then the determinant of the whole matrix is going to be 0. So we know that the determinant of this is going to be 0. So what if there was an inverse of this? that would mean that this times its inverse would give us I. So it means that this might be, we'll call this A. So A times some other matrix is going to give us I, but we just said that the determinant of I is 1. The determinant, and we also showed that the determinant of A times B is equal to the determinant of A and the determinant of B. Now, we didn't show that, but we accepted it. So, so the determinant of this is going to be 1, but the determinant of this is also equal to this times that, but this one we already said 0, so this can't be 1. So, okay, so if there's a column or a row which is all zeros, then we can conclude that there can't be an inverse. Now, this is going to be this previous one is going to be kind of hard because you're going to have to make another matrix over here, give it arbitrary name like B1, B11, B12, B13, B21, B22, B23, and so on. Then you're going to have to multiply this all out as matrix multiplication. Each element is, then you're going to have to set each element. So you're going to have like 9 different equations to solve to find out the inverse. So that sounds like a terrible problem. You might try it with just a 2 by 2 matrix instead of 3 by 3. Then you'd only have 4 equations. So the next question is about whether the inverse is unique. That is, we said A is invertible if there's a B, such that when you multiply A times B, you get I. But could there be 2 different B's that work? That is, when you multiply them times A, either one of them will give you the identity. But this would mean that A, B1, if that means we have 2 inverses, B1 and B2. But that would mean that AB1 equals I and AB2 equals I. That means they're equal. But I think pretty sure we had a matrix multiplication property that says that if this is equal to this, we can cancel. So that would mean that B1 has to be equal to B2. So there can't be 2 separate ones. So since we can't have 2 separate inverses, then we can just write A inverse, and that's the unique inverse of a non-singular matrix. So it has. We only do this for we're talking about matrices that have inverses, and we can write this as a name of the inverse. Okay, the next one is, they say, suppose that we have 2 invertible matrices. A is invertible and B is invertible. You might ask, what about their product? Is it invertible? And they say, show that the product AB is invertible, and that its inverse, the inverse of AB, which we can write like this, we denote it like this, is equal to this. So the easiest way to do this is to take a clue from what they already gave us here and just show that if we take AB times this, we do get I. So one thing is, first of all, can we write B inverse? Yeah, because we said that B has an inverse, so this is the inverse. Can we write A inverse? Yeah, we said that A has an inverse, so we can write A inverse. So what they're saying is, does AB, the product, have an inverse? So that means, so yeah, it does, because if you just take AB times this, you're going to get I. That means this is the inverse of AB. Or you can try that very quickly. If you write AB, if I wrote A, B, and then B inverse, A inverse, well, let's write it. So if you write that, then of course this is just I. So you have A, I, A inverse. So AI is A. So you just have A inverse, but that's I. So this is equal to I. So we can say that the inverse of this is this. Okay, and next one is show that if A is invertible, then its determinant is not equal to 0. So this is we can prove this, but actually the converse of this is the more interesting part, which is if the determinant of A is not equal to 0, then A is invertible. That's more interesting because that tells us a condition when A is invertible, if the determinant is not equal to 0. And the other direction shows us that if it is invertible, then also the determinant is not 0. But anyway, how do we prove this one? So we say that A is invertible means there's an inverse. It means that A times its inverse is equal to 1. But then the determinant of this is equal to the determinant of this. But we know the determinant of this is equal to 1, so this is equal to 1. But we also know that we can split this as the determinant of A times the determinant of A inverse. And we have that equals 1. Then neither of these could be 0. So that's how you show A, part A. And then that also shows this one, because we just showed that this equals 1, but that means that the determinant of A is 1 over the determinant of A inverse, or vice versa. So that's this. Okay, the next thing is quite useful for 2 by 2 matrices. It's not true in general, but for 2 by 2 matrices, this is very useful. It says that if you have a matrix like this, then you can find the inverse. The inverse is going to turn out to be this. So if you start out with this one, A, B, C, D, like that, the inverse is going to look like this. So first of all, what's this part look like? So we switch the A and the D, so we have D and A here. We don't switch the B and the C, but we put minus signs in front of them. So we get DA switched, and then minus B and minus C there. And then we have to multiply by this, which is 1 over AD minus BC. But what is this AD minus BC? That is, I think we've seen that somewhere, that this is the determinant of this matrix. So we're multiplying by 1 over the determinant outside here. And then we did this kind of switching over here, and that gives us the answer to the inverse. The inverse. Okay, so if the matrix looks like this, we can find the inverse, as long as this part here, AD minus BC, is not 0. And then use that to find the determinant of this. So you could try that. Now here, this is a bit messier. If A is a 3 by 3, then, what was that? Squiggly underline. Ooh. Okay, if A is a 3 by 3, then the inverse, as long as the determinant is not 0, let's try that again. As long as the determinant is not 0, then the inverse is 1 over the determinant, so that's why the determinant can't be 0, and then times all this stuff. So anyway, this is kind of a formula for finding the inverse of a 3 by 3, but it doesn't look particularly easy to do. But you could try it on here. Okay, they call this kind of construction, which is a matrix actually, right? Because this is a determinant, this is a determinant, this is a determinant. So this kind of thing, they give it a name, this whole matrix. It's called, given a matrix A, this is called the adjoint matrix of A. So what is it? It's so we have A11, A21, A31, A12, where these are the sub-matrices. So A11 means if we started with A11 is this matrix here, and A1, 2, A1, 2 would be 0, 1, 4, 3. That would go here with a minus sign, and so on. So the inverse looks like this, and this is called the adjoint. So they say more generally, even for any n by n matrix, the inverse is going to be 1 over the determinant, this part, times the adjoint A. So the adjoint A is a matrix. We construct that matrix. We do this, and we get the inverse. So, I mean, constructing that matrix is not necessarily easy. We have to calculate all these determinants to do it. But once we've done that, we can construct this matrix and then take the original the A and get its determinant, and then do this, and this will be a new matrix which will actually be the inverse of the original A. And they say this is, kind of a theoretical result. It's not so practical because there's a lot of calculations to do it this way. Okay, the next thing is the cross product in Rn. Well, we're not going to talk about that.